Guys, I think we are live. You can go ahead.
Can
Yeah,
we
I
go ahead?
see Shankar's. Yes, yeah, I see Shankar's PPT page.
All right. So you let me know you want to give an intro and then we can start.
Yeah, I'm just waiting to see if a few more people join in on.
Yeah, Nandan, you let me know. I think you decide what is a good time and then
Okay. Vishwa, there seems to be a lot of lag, especially audio lag.
No, that is fine. And then both audio and video will be synchronous. So there's a lag,
Okay.
but we can't do anything. You go ahead. The YouTube video will catch up.
That's fine. Okay.
Nanda, I think also one of you need to verify that the video stream shows only the video stream from my side and nothing else. Not the Zoom control panels or whatever, right?
No, it will show whoever is talking, I think. But as long as you are talking, everyone unmuted, it will show whatever you are presenting.
Okay.
Let's wait for another 3 or 4 minutes, and then we get started.
Okay.
All right, let's get started. So, welcome everybody. First of all, good morning, good afternoon, good evening, depending on which part of the world you are connecting from. My name is Nandan Narasimha. I'm a volunteer with the Bangalore Astronomical Society. Bangalore Astronomical Society is thrilled to welcome you to their talk about the total lunar eclipse. As you already know, the world is going to witness a total lunar eclipse tonight, visible from Western Australia all the way till Eastern Africa. This partial eclipse starts a little before 10 p.m. Indian Standard Time, with totality lasting a little over an hour 20 minutes. The partial eclipse ends around 1:26 a.m. on Monday, and needless to say, this eclipse is visible from all over India. We strongly urge you to step outside, view this cosmic spectacle. Get your family and friends along too. There's absolutely no need for any equipment to enjoy this, what is called the dance of the shadows that our cosmic neighbors are going to put up tonight. All you need is clear skies and an open mind. Remember, the next total lunar eclipse visible from India is only in December 2028. So that's over three and a half years from now. Coming to today's talk. Today's talk is titled Celestial Shadows, Unveiling the Depths of the Lunar Eclipse by K.V. Shankar. With a master's from IIT Bombay and a career spanning 25 plus years across industry domains, Shankar has an avid interest in astronomy, space, and space sciences. He has developed simulations that were used by ISRO for their Mars and Moon missions. In today's talk, he will explain what causes a lunar eclipse, what a total lunar eclipse is all about. So, if you ever wondered why you don't see an eclipse every full moon, now is the time to sit up and listen. Is it safe to watch an eclipse without eye protection? What's with the reddish color of the moon during an eclipse? Get to know all about it from this talk. So before I hand off to Shankar, a request to people on YouTube. Please do post your questions in the chat window and we will answer your questions at the end. So Shankar, it's all yours.
All right. Thanks a lot, Nandan. So first of all, my sincere thanks to the Bangalore Astronomy Society for organizing this and giving me a good opportunity to talk about today's eclipse in this session. So we will get started. So as Nandan said, we are going to see what an eclipse is, what is a lunar eclipse, what is the geometry involved, what are the phenomena involved, principles involved. All right. So that's the core of the talk and a bit about today's eclipse. So as Nandan said, please post your questions. If you are watching this live, please post your questions to the YouTube channel. We'll pick them up after every section of the presentation. All right. So that is the overall plan. Okay. So let me just quickly cover, what's my goal of this talk. So we all know how eclipses happen. It's school physics, nothing new there. We also know about phenomena like scattering and other things. Most of you would know that. So what's the goal? So our goal is to connect all these foundational principles, which you already know, right? And put them in a way so that I hope to create a few aha moments from that, right? And together, we want to get a deeper understanding of what a lunar eclipse is. All right. So that's the plan. So with that, a few topics which we'll cover today. We'll start with an intro, and then we'll get into comparison with phases of the moon, why lunar eclipses typically occur only on full moon, right? And we will get into some geometry about the shadows. What is the nature of the shadows, in the sense how dark it is, how long it is, what is the shape of the shadow, how does it matter? We'll get into that. And one interesting phenomenon we can see on lunar eclipses is the reddish color, right? Reddish orange color. Some people call it copper moon, some term it blood moon. Regardless, why is that color coming? All right. And we will end with some details of today's eclipse. So based on how we go, what questions come up, I may show some demo here. I'm not sure how the setup can be streamed live, but if things work fine, yeah, we might spend a few minutes doing a bit of a small demo. But otherwise, we'll run through this session. Okay. So on a lunar eclipse, right? Let's start with what is the progression? What do we see, right? So I've shown a picture here, okay, of a lunar eclipse from 2018 Feb. This was shot from an observatory in Arizona in the US. And this is in fact a composite picture, right? You can see that there are multiple images of the moon. And this whole eclipse lasted several hours, easily 4 or 5 hours. And the photographer has captured right from the beginning at the very top. He has done that. Let me use a highlighter. From the very top, where the partial eclipse starts, all the way down, the umbral eclipse progresses, and then we enter the total phase, right? And that is when the moon becomes red. So that is a typical progression. So if you pick another picture, this is again another picture showing the same progression. This is from a 2014 eclipse. But here the photographer has used the liberty to increase the size of the moon for artistic effect. But otherwise, we see the progress as such. It progresses from partial starting to near totality, totality up roughly here, and then goes all the way. Moon comes out of the shadow. Okay. So one of the things you should note is that where does the shadow enter? So we have seen the moon. We are familiar with its shape. If you observe the moon, people relate to some hare or rabbit being on the moon, with this being the head, the ears of the rabbit. This is the body, right? This is the east of the moon. This is the west of the moon. Okay. And this is north and this is south. So the shadow typically enters the west side of the moon. Okay. From our point of view, it will be toward the eastern horizon, but from the moon's point of view, it's west. Typically, it enters from the west because it in fact traverses the shadow, right? Moon goes around Earth in anti-clockwise direction, and if you work out the geometry, that's how it is, right? So it typically enters in that way, and then it exits. Finally, the last part, right? This part is towards the east. You can also see that, we can see the moon sort of turning around as it goes from rises and sets, the usual phenomenon, which you observe, right? You just turn your head. So that's what happens when you photograph in this way. It's another picture. This is again a progressive picture. We're not covering the entire eclipse here, but only until the totality, right? And at the totality, we get the red tint. This is the full eclipsed moon, copper moon, taken with the right exposure. So in the real life, if you happen to see it tonight, hoping for good weather, it'll be, of course, not be this bright. When you really see, it'll be much less bright. In a photograph, you can always put the right exposure so that the fully eclipsed moon appears to be as bright or slightly less bright than the full moon. But in reality, there will be a small copper tint. It will be dark, but you can definitely observe a red tint. All right. That's what you will get to see. All right. So now, how does it occur? We all know, we all studied. So there's a quick animation coming up. This is from NASA. So you can see the moon revolving around the Earth. This view is from the north. So you can see this is the North Pole. And you can see Greenland. You can see the American continent, the Asian continent here, and you can see the eclipse. So if I were to play that once again, you can see here, it enters the shadow, almost remains completely in shadow for some time and exits. Okay. You can see the same shadow up here, right? So one of the things to note is that there are different shadows, right? I mean, it's different views to see the shadow, right? So there is this sunlight falling on Earth, and on the night side, we are in fact in Earth's shadow. What is night? Night is nothing but absence of light. That absence of light is created by Earth itself blocking the sunlight. So somebody on the night side, they are in fact on Earth's shadow, right? That shadow extends all the way beyond Earth to nearly 3 to 4 times the orbit of the moon. Okay, that shadow is that long. And if the moon gets captured in that shadow, we get an eclipse. So it is the same shadow. If I am on the Earth, on the night side of the Earth, at night, I am definitely in Earth's shadow, but we typically don't say that I'm in Earth's shadow. I'm eclipsed. We just say it's nighttime, right? But then if you take a space station orbiting the Earth in this way, right? Of course, they say they are in the shadow, they are in eclipsed, right? Same happens with moon. Moon being a satellite, when it revolves around, it gets captured on the shadow side. You get a lunar eclipse. At the same time, there is a from the moon, from the perspective of the moon. Uh, if you happen to be on the moon looking up towards the sun and the earth, you get a solar eclipse. The sun gets, obstructed, obscured by the earth. It becomes dark, and you get a solar eclipse on the moon. Okay. So in a way, it's a combination. It's a pair. So there is a lunar eclipse on the earth, seen from the earth. And if you happen to be on the moon, you get a solar eclipse, right? That's how it works. Let's move on and let's switch to another animation, which shows the shadow in a more 3D perspective. So I'm going to play that. This is again from NASA Visualization Labs. We'll share the links in the video after we post it, so you can take a look if you want. It's a nice video. Again, let me just play that again. Revolving Earth, and it enters the shadow, and it stops at totality, right? We will see other videos and visualizations afterwards. So briefly, what you have seen is that this is the like a static picture. All right. So these are the beginning of the eclipse. Partial ingress phase begins. We call it ingress, not just partial phase, because it's the beginning of the eclipse, right? You want to distinguish between the entry and exit. So you call the entry as ingress to distinguish. So you can see a bit of the shadow again on the west side. Move forward. Now it is fully in the shadow. This is the complete dark side. You can see a tinge of light because I put it this way at the edge, very edge, right? Total eclipse is just about to start. It moves forward completely in the shadow, fully eclipsed. Now it's about to exit the deep umbral shadow. You can see a tint of light, and then it almost comes out, right? That is a sequence. So this is very straightforward, basic physics. I have simplified this diagram so that I am showing only the umbral shadow, the deep darkened shadow. We will come to the umbra penumbra distinction a bit later, right? For all practical purposes, for lunar eclipses, only the umbral shadow matters. Umbral shadow is where the complete sun is obscured when seen from the moon, right? So there's no light, not even a bit falling from anywhere from the sun. But of course, as the moon traverses, there will be time intervals where the sun is only partly obscured, and there will be a dimming of the light falling on the moon. That dimming of the light is generally not visible from Earth. Okay. Unless it's completely in the penumbral region, it's not visible. So usually people cannot make out, yeah, I'm having a penumbral eclipse because it's just dimming. There's no darkened shadow which we can see on the. So to keep things simple, at this stage of the session, I'm just showing the umbral shadow. All right. So that's what happens, at that time. So that's a very basic quick run through of what we can expect, what is the progression. So Nanda, I just want to see if there are any questions at this stage. If not, we'll move to the next segment of the presentation.
No, Shankar, no questions yet.
All right.
Let's go ahead.
Let's go ahead. Yes. So question usually comes, why is that what is the pattern to lunar eclipse? When do we typically see? Does a lunar eclipse occur every full moon? Why or why not? Right. So one of the questions often asked is, if what is in fact a full moon? Full moon is when we typically say moon is opposite the sun, right? If you take the sun, earth, moon angle, um, we tend to believe it is 180 degrees, right? That's what a face is, right? So the face angle is 180 degrees. The moon is directly opposite the earth. Then why is it that it doesn't occur, right? So that's what we are going to address next. So the phase, this demonstration is quickly a recap of moon phases. It shows on the left a view from top at an angle, the moon revolving around the earth. And you can see sunlight falling from the top, this direction, top to bottom here as well, right? You can see the sunlit portions, bit like a crescent. And this is a view which we view from, earth. So this is the face. So face, what are we exactly seeing? So this is the daytime portion of the earth, lit portion. This is the unlit portion, nighttime. This is the daytime portion of the moon. This is the nighttime portion. It is unlit. So it's a day and night, right? So 50% daylight, lit portion of the moon, 50% unlit. So if we happen to see at an angle where we are seeing the full lit portion, if that is the orientation, then we can see a full moon, right? So full moon, new moon, quarter moon, they're all about orientation or perspective from the earth. There's nothing different on the moon itself. Moon is 50% lit, 50% unlit, 50% day, 50% night. It's always the case. It is just that how you view it, right? If your view changes, you get to see only some portion, either 0% if you are on the unlit portion, if you're watching the unlit portion, you don't get to see anything, right? So that's new moon. That's about it, right? So that's the usual phases of the moon, right? It's just that you're looking at an angle. There is not any earth shadow or anything happening. You're just seeing the mix of the daytime and nighttime of the moon. Okay, that's the lunar phases. So that's what I'm showing here in this slide as well. That the phase angle changes, right? It goes away all the way from new moon 0 degrees roughly to 180 degrees phase angle, right? So here the angle which we typically use is the ecliptic plane. We define an angle on the ecliptic plane. So if the lunar longitude is the same as the solar longitude, that is new moon, and if it is 180 degrees opposite, it is a full moon. So since we are talking only in one coordinate, the longitude, and we are not talking about latitude, right? That's what makes a difference. That's what decides whether we get a eclipse or not. So the next demo video will show you why that happened. So you can see here, I'm going to play that. It will reach a configuration as if it's going to be a lunar eclipse, but then you will see that it is really not. So here you can see that this visualization is to scale. So Earth and Moon are shown to scale. The Moon is about 1/4 size of the Earth in radius or diameter, right? It's 1/4. And the Earth shadow, goes a long way. It's a cone. This umbral cone goes all the way up to 3 or 4 times the orbit size, this size. So if this is X, it extends up to 4X roughly. And interestingly, the moon shadow, is just about the radius of the uh, lunar orbit. That is material for getting good solar eclipse, but for this lunar eclipse, let's not worry about that. But it's an interesting fact to note here. So if I run this animation, you can see that it is going around. It's about to cross the shadow, and we might think that might be an eclipse. We are zooming in on that region, and then we will tilt, we will bring the camera down and looking it sideways. There we see that, hey, it's not really in the shadow. It is just that because the orbit is tilted, I really don't cross the shadow and I don't get an eclipse, even though it was full moon, right? So that is why we don't get to see lunar eclipse every full moon. The moon's orbit is about 5 degrees tilted with the ecliptic or the Earth's orbit around the sun. So as you can see in this diagram, here, wherever there is a new moon, here you get a solar eclipse. It's in a straight line. And on the rightly on the opposite side, you get a lunar eclipse. And this plane of the lunar orbit, right? The lunar orbital plane, as you can see, it is a 5 degrees tilted with the plane of the ecliptic where Earth moves around the sun. And because of that angle, in this geometry, yeah, you get an eclipse, a pair of eclipses. But this orbital plane remains at the same angle when you rotate and comes here. And now here you don't get it. And again back after 6 months, after 6 months from the original point, you may get another pair, and then here again, no, right? So that's the typical geometry, simplified geometry. Now here you can see that this plane remains the same. The angle remains the same in this figure, right? It's tilted in the same way, looking at an axis which is here, something like this. But then that is not the case. That plane has a precession, and these intersecting points, which are called nodes of the lunar orbit, they have a precessional motion or they have a retrograde motion where they tilt a little bit. So as we find later, we will see that this is not exactly 6 months it'll align, slightly earlier. All right, okay, slightly earlier. But that's a small detail to worry about. But the main understanding is that we don't get a lunar eclipse every full moon because of the tilt. Okay. So now that is the same reason why we also have partial lunar eclipses. So we may have a full moon, no eclipse. We may have a total lunar eclipse, in which case the moon gets fully immersed in the shadows. Or it may so happen that it may just graze through the shadow a little bit and you get a partial lunar eclipse. Today's eclipse is a total lunar eclipse. So this is the geometry where it's just partially, this view is from the side, okay? And we get a partial eclipse. So now, that sort of covers this second part where we talked about moon phases and eclipses. So let's see if there are any questions, Nandan.
No, Shankar, nothing yet. Let's
Nothing.
let's proceed.
Let's proceed. All right. So the next segment, we are talking about shadows in depth. All right. So this is where we put together some of these interesting aspects and see what do we get, right? So we all know the principles, but we may not have thought along those lines. So this is where we get some more deeper into the geometry, all right? So look at this picture. So this is like a dark patch, almost novel patch, falling on the moon. Do we see the lunar eclipse in this way? Do we get to see it this way? We don't. So, and why is that? So we will answer that question in this segment. If you take solar eclipse as seen from the Earth, shadow falls something like this, but not exactly this big. It definitely is a much, much smaller shadow on the Earth's surface, right? But then on the moon, lunar eclipses do not happen this way. It is not a patch. Moon is fully obscured. Why is that? Right? And let's look at why that is so. So here you can see, did I switch the... Yeah, okay. As you saw this um, picture, right? 5-degree inclination. Is that 5-degree enough? Okay. In the animation, I know it's more like 20, 25 degrees. It's really not 5. So when we say 5 degrees, does that 5 degrees make a difference? Right? So that is one question we should see. Okay. So now why we don't see a patch shadow on the lunar surface? Why is not a small circle which we see? The main reason is the geometry, right? So here, this is to scale. Okay, so there is Earth shown here. Earth's diameter is about 4 times the lunar diameter. So that's why I've shown 4 moons on the left side to get an idea of how big they are relative to each other, right? And the shadow from the Earth, right? The umbrella shadow, as I said, it is very long. And on the right hand side, I have shown the moon, which is about 400,000 kilometers away, right? So here, this Earth's diameter, the distance to the moon, and the moon's diameter itself are shown to scale. And this shadow gets narrower and narrower as you progress outwards into space. It is in fact a cone, right? But at moon's orbit, as I said, this shadow goes all the way up to about 4 orbital lengths. But at moon's orbit, it's about the diameter of about 3 moons, not 4, 3. 4 when it starts, 3 at lunar orbit length. Why is that? Because the sun is a very large extended source of light. And because of that, this shadow, umbral shadow, is getting narrower and is in the shape of a cone. The exact angle is half a degree, right? The exact angle at the apex is half a degree, which is the angular diameter of the sun seen from near the Earth Moon system, right? That is the angle you will see. So because of that, it's 3 moons. Because it's roughly the diameter of 3 moons, you will not see a patch falling on the moon surface, a patch of shadow. It'll always be a large shadow obscuring partly in the beginning and then fully afterward, right? So that's why you don't see a patch. And in this figure, I also marked 5 degrees inclination, right? So you can see what is the kind of distance it places the moon at, right? It's quite far apart at this point. So 5 degrees is more than enough to avoid any eclipses in most of the full moons, all right? Here there is some metrics to let you know how they relate to each other. You can look at it, all right? So now let's look at it again from a size and scale perspective. The universe is very huge. And this is one of the very, very interesting facts when you see that, right? So here, if I were to show a model of the universe with some styrofoam balls, I pick a small ball, 10 centimeter diameter, right? Moon is about 1/4, so 2.5 centimeter. I have to keep them about by 3 meters to get the scale right. And if I use the same size balls, right, I need to keep the sun roughly 1.2 kilometers away, right? And that sun is as huge as 10 meters diameter. So that is the scale you are looking at here. 100 times Earth's diameter is sun's diameter. And here the Earth moon orbit is 3 meters in the scale model. It is 1,200 meters, 400 times in the whole scale of the universe. So at this scale, you need to know the geometry to predict the right pattern of eclipses happening, the kind of geometry, the kind of shadows you get, and how often you get. Right? This is the geometry you need to be aware of. Right? So this geometry also plays when you see, how large the umbral shadow is. Right? It's about 2.7x in angle. So the moon is about half a degree angular diameter when seen from Earth, and the umbral shadow is about 2.7x. So you can say that it's about 1.35 degrees, 1.3 to 1.4 degrees based on how far the moon is. It's in rotating around the Earth in an eccentric orbit. So that distance varies. So this diameter of the shadow also varies a little bit. So that changes the kind of eclipse you get, right? But this is some fact to know about the lunar eclipse, all right? So now that also means that we can sort of imagine a circle coming right onto the moon to create the shadow. And as it progresses, you can see this big circle which I have shown, that is the complete umbral shadow getting into the moon. Okay, that's about 2.7 times, and you can see that the curve fits. I've drawn the exact animation with roughly 2.7x size, and you can see that the curvature exactly fits. So this is something which you can see recognize as a pattern, distinguish if somebody shows you a picture of the lunar eclipse or a crescent moon, you can easily tell, hey, this is a phase of the moon or this is in fact an eclipse, right? You can detect any uh, pictures that have been claimed to be an eclipse, but really it's just a crescent moon, right? So now, interestingly, that also gives us some photographers a great opportunity to picture the eclipse like this. So this is again a composite, but they show a large circle in the composite. This is the umbral shadow, and they align the moon's partial eclipse pictures in such a way that you get to see the complete umbral shadow like this. So when the moon is entirely in the shadow, it's a complete total eclipse, right? It gives you interesting ways to photograph the eclipse, where you can see the size of the umbral shadow. If you move forward, this is a crescent moon, right? It's not really a lunar eclipse. Why is that? So you can superimpose a circle. This is the full circle of the moon. And then what we call the terminator, right? The terminator line. This is the terminator line where the sunlit and the daytime, the nighttime portions of the moon converge, right? This is where sunrise is happening, sunrise or sunset, right? This is the terminator line. And here you can, if you were to draw a line, if you draw a curvature, right? You get a squished circle, which is nothing but an ellipse. So if that is what is the shape of the curve, you know that, hey, it's a crescent moon, just the face of the moon and not really an eclipse. Same here in this gibbous moon, right? You imagine a circle around it, squish the circle as if, you are not seeing a full circular plane, but at an angle. You tilt it, you get an eclipse, and that matches exactly the terminator line, right? So that is why it is the face of the moon. It is not a shadow of the earth falling on the earth. But if I compare here on the left side a gibbous moon and on the right side shadow coming in, then you know that you can imagine the length of the shadow, length of the curve. There you see the difference. This is not a squished circle, right? This is a much larger circle, easily 3.5 times, roughly 3 to 4 times, right? And then you can see that, hey, this is an eclipse. Another giveaway is that, here the shadow is just ingressing, right? Why do you say it is in ingress and not really an, egress? That's because this is, you see the hair again, and you can see that this is the east of the moon and the shadow is on the west. So this is ingress, right? This is ingress. So, and whereas, this is about 20% shadow. So 20% shadow you won't get in this way for a face of the moon. All right. So all the geometries are giveaways, easy clues. This is a nice graphic. So this is from the American Astronomical Society. They have put together a nice graphic showing, hey, what's the difference, right? We all know intuitively, hey, both are different, but it's nice to compare that, how things differ. So the comparison is in 2 dimensions, right? One is about the shapes of the shadows, shape of the shadows here, um, across the progression, the timeline here, right? How long it lasts, partial phase lasting roughly an hour, a full totality lasting about 1.25 hours. Again, the egress, right? Time goes from right to left here, okay? Whereas in the phase, it's 29.5 days, and you get to see the difference. So you can see the curvature here like this. Whereas if you take an equal moon somewhere here, right, it is a different curvature, all right? You can easily figure it out. Even in the absence of the reddish tint, you can figure out what is really happening. Okay. So now, so we were digging deeper into the structure of the shadows. All right. So we have looked at how long is the shadow, how wide is the shadow at the orbit, at the distance of the orbit. Correct. An aspect which you have not touched upon is the whole umbra penumbra thing, right? So let's look at that. What exactly is that? So typical school textbook will show this diagram. All right. and you will see this pattern geometry here. They will draw a line from this edge, another edge, 4 line. Then they say this dark pattern is umbra, and this is penumbra. So what exactly is that? And can we get to know more about that? So here we have shown a partial and a total eclipse here. So the typical pictures you will see in textbooks. So what is an intuitive notion of the penumbra umbra, right? Can we get to know better? Yes. So umbra and penumbra have to do with the source of the light. What is the size of the light source, right? This has nothing to do with Earth or Moon. It is just the size of the sun, so the angular size of the sun, right? So if the source was point source, I will get a shadow like this. It's a diverging cone. It is not a converging cone. It's a diverging cone. Because if I draw straight lines, there's nothing, no way that straight line hits the Earth and then somehow emerges, or in the natural sense, assume for a moment that there's no atmosphere, no refraction, the light won't bend, right? So I can't have a light coming here and then bending and getting into the shadow. That won't happen. Nor here. Forget about gravitational attraction, whatever, right? Very, very small, tiny, tiny, tiny effects. So in this case, we get a typical expanding cone geometry, right? So there's only two distinctions here, two kinds of, either it is completely in the shadow, or I'm completely lit. So that's what I've shown here. This is the Earth obscuring the sun. The sun is shown in dotted lines, right? It's not really visible. It's fully dark. Just for demonstration, I put it as a dotted circle. If you go up, if you see from this vantage point, the source, of course, it's visible. There's a line of sight, and you can see the point source of light here from this point. If you are here, you can see the point source of light. But sun is not a point source of light, right? It is, in fact, an extended source. So it is as if there are, infinite number of sources here. But what matters is the sources on the edge, the tip, right? So how do they matter? So let's look at, suppose imagine a light source here at this tip. It will form a cone of shadow like this. Even now imagine another tip here. It will form another extreme, right? It will form another shadow. But then you get now three distinct regions: fully lit, partially lit, this is, or partially shadowy, right? Completely in shadow. In no way I can see the sun. It's fully blocked. And here, it's partially blocked. This is what we call umbra and penumbra, right? So now it is only due to the fact that it is an extended source. So if the sun were not an extended source, this won't be the case. And for lunar eclipse, it really doesn't matter, right? Let's look at that. Why? So now I put an additional, annotations here, as what we can see. So now if I were in these points, right, what would I see? So now I am assuming that I am at this point, in 5 different points, right? So if I'm here in the light, obviously I will see the full sunlight, full disk of the sun I'm able to see. If I'm here in this point, I can see the bottom of the sun, right? I can draw a straight line as much as I can. And that will probably hit here, but not beyond that. Right? Not beyond that. So I will see bottom of the sun, like a crescent sun. So I'm in fact having a partial solar eclipse here. And here, it's fully obscured. At this point, again, a partial solar eclipse, right? I'm getting sunlight, some light. And here it's full lit, right? So that is the next step in understanding what's really going on, right? So now let's make one more change, right? Now this is an extended source, but this point where the shadow is falling, it was a point object. What if we extend it? So real moon is extended, right? Real moon can be anywhere here, and we get from here, we get to see the full disk of the sun, right? It's fully lit. When I'm in position 3, I will get part of the sunlight is obscured. Okay, I get to see a light shadow. Why a light shadow? Because the sunlight is cut out. Maybe 50%, maybe 60%, maybe 10%, right? But the sun is so bright that even 10% light falling on the moon gives it a lot of brightness, and it's very difficult to detect this change, this dip in the brightness. So this shadow, the penumbral shadow, very, very, very difficult to spot. except you can spot only when it is deep into the penumbral shadow and it is covering, most of the moon. Then you can probably detect or measure it, but mostly you just cannot detect it. It's a slight reduction in the brightness, right? And in the fully eclipsed totality phase, from the moon, obviously the sun is fully obscured, and we get to see of course it should be dark, but it is not. We will figure out why it is so. There is a bit of a light coming. Light is bending, the red light is bending and falling on the moon. That's why we see a light tint. And when you go up 7 and 9, again the reverse. You see a bit of the sun, and then dimly lit moon, slightly dimly lit moon, and then full moon, right? So this is the effect of the umbra and penumbra. All right. So we all have seen the diagram, but it'll be good to relate if you see from the moon what really happens, right? But I've specifically excluded the edge cases here, right? Let's look at the edge cases now. So if I go to the edge cases, that is when I am one leg is here, one leg is there, right? That is the case I'm talking about. So 2, 4, 6, 8, right? Case 2, I am partly, so case 2, what does case 2? What is case 2? Moon is an extended object. So part of the moon is fully lit, part of the moon is partly lit. So you get to see, depending on where you are on the moon, you get to see two different shapes of the sun. On the part on the bottom of the picture here, you get to see the full bright sun. That is why this side of the moon is fully lit. But if you are on the penumbral side, like you can see this arc here, slightly dimly lit moon, you can see partly obscured sun. So you can imagine this progression, you can work it out. And as you progress at 4, we have penumbral shadow here, umbral shadow, dark shadow. So this is partly lit, this is completely obscured. And then it reverses and you get the full picture, right? So this is what happens in a complete eclipse, right? This is a full picture, umbra, penumbra, and how it matters, right? So this is the story there, okay? So now we have finished another segment, all right? So now let's see if there are any questions.
Nothing yet. No questions yet. Let's go ahead, Shankar.
All right, let's go ahead. So now the next part is about moon color. All right. So the moon color, why is it red? Why is it a distinct? So that is happening because there is a thick atmosphere around Earth, and that atmosphere does two things. What are those two things? The first thing is that it scatters light. So there are multiple phenomena happening. One phenomena is called Rayleigh scattering, where very small molecules, which are roughly the size of 1/10 or even less the size of the wavelength, right? They scatter light. So, and they prefer to scatter the higher frequency or lower, wavelength light on the blue side, right? They scatter it more than the higher wavelengths, right? The scattering is in fact inversely proportional to the fourth power of the wavelength. That's what Rayleigh scattering does. So that is why you get to see a blue light. I mean, blue light from the sky. Why is the sky blue? Because all the small molecules on the upper atmosphere, they scatter the blue light more than they do any other wavelength. So when things get scattered, you get to see that object, right? You see an object because either it reflects light falling on it or it scatters light in all directions. So some direction may be towards your eye and you see that light. That's what happens when you look at the sky. Sky is blue. And the same phenomena is happening here as well. And all the blue light is scattered away. It's taken out from this full spectrum. The full spectrum has all the colors. You remove blue and higher wavelengths from it. What do you get? You get light which is reddish in color, right? You remove the blue portion. You subtract. But then how does it get into the umbra side, right? Yet it has to bend. That bending is also a very well-known phenomenon. You definitely would have seen it at sunrise and sunset by seeing the sun at a oval shape, right? That is, or a mirage on a desert. So light gets bent because of refraction. So the atmosphere it has to go through, right? It acts like a real prism and bends the light. And that bending, red light, of course, gets bent more, and it gets into the umbral portions, right? So it gets all the way, even up to the axis of the shadow, and right. So two phenomena acting together. One is the scattering of the blue light. So you end up with light minus the blue part of it. The second is that it gets bent. All wavelengths, even very tiny portions of the whatever blue light remaining, they also get bent, but to a lesser extent. All together combine to create the effect that you end up with a small reddish tint on the moon. That is why you get reddish color, right? This also depends on other particulates in the atmosphere. So you can find uh, volcanic dust, smoke, water vapor, a lot of things. They all add to the phenomena, and they all contribute to the exact nature of the redness we see during a total lunar eclipse. So 70s probably, I think there were some volcanic eruptions, and that resulted in more reddish color. But now that's not the case. We'll have to see, hoping weather is good, hoping we get to see a good lunar eclipse. We can see what kind of red. Has somebody seen this color? How is it to be on the moon at that time? 12 people have walked on the moon, but they have not seen any lunar eclipse in the late 60s, 70s, right? But a spacecraft has seen a lunar eclipse, a solar eclipse. From the moon, a lunar eclipse on the Earth, right? What was that spacecraft? It was a Blue Ghost. It's a private provider called Firefly Aerospace. That craft landed on the moon in March earlier this year. And 6 months earlier, right? Exactly, there was a lunar eclipse. And it so happened that it's captured it. And this is a picture, which it has captured. There are two pictures I've shown here. One is there is more light. You can see all of it is in reddish hue, right? And here you can see a tiny sun. It's in fact the diamond ring effect being seen from the moon. Okay, that is also reddish tint in color. And you can see it's almost dark. You can barely see sun getting. You see the point here. See the same point here, right? These are the points getting reflected. Barely any light. Right. So it captured a few snapshots of a solar eclipse as seen from the moon, which is in fact a lunar eclipse from our perspective, right? So this is an interesting capture there, all right? So that is the end of the segment where we talk about color. So we can move to the next segment. And then if there are no questions, if there are questions, we can take it up.
No, Shankar. Let's move ahead.
Let's move ahead. All right. So this segment talks about how do we predict eclipse. Okay. So there were science has progressed over the years, over the centuries. So earlier humans, right, in earlier times, people used numerical methods. So they observed the cycles. Can I see a pattern here? If I see an eclipse today, in how many days will I see another eclipse, right? So they kept records. They kept this pattern. They tried to find, what is a pattern emerging out of it, right? And they were indeed able to find patterns. Why? Because all this phenomena is based on cyclic movements, right? A rotation of the moon around Earth, which has a specific period. Uh, when the moon crosses the nodes, that has a specific period. When the sun crosses the nodes, all these have specific figures, right? Even though they may vary a little bit during a long time of several centuries, they all average to a number very close. And the deviation is not much. Like if you take a moon, lunar month, roughly new moon to new moon, 29.5 days. The variation across 2 months is probably a few hours at most, right? 6 hours or fraction of a day. So you can work out numerical patterns, empirical patterns, and with that you can predict. But those predictions were not accurate in the sense, it was off by a few hours. And they were not able to predict the exact location where it would happen, right? So that was the situation. But then things have changed from 17th late 17th, 18th century. We have Newtonian mechanics. We can predict with very high precision what contributes to that. We have a good solid theory of how objects move, what are the forces involved, what is the gravitational force involved. We can predict all orbits to a very, very high precision. And we can also, for that prediction, use physical constants like masses of various planets, distances, angles, all measured more and more accurately over time, right? So we have a solid backing um, in terms of the constant which you use, in terms of the initial position which you use, which can keep iterating, which you can keep revising. And we propagate from that measurement, run a numerical integration to run Newtonian mechanics or even general theory of relativity and predict what would be the position and velocity in the future, right? To whatever accuracy we need. And we have very accurate models, right? That's what we do wrong. And there are ephemerides from JPL and others which are disseminated to the public. We can use that. Even, calculations are available in, tools like Stellarium. You can compute eclipses there. All right. So we talked about these patterns. If you want to dig deep, if you are interested more to know how do we calculate, some of the things to start are, what is a draconic month? Node to node, how long does it take? Perigee to perigee, how long does it take? The closest point in lunar orbit to another closest point, or a new moon to new moon. All these are in play in determining what is a cycle, right? So one typical cycle is eclipse year, 346 days. These are time sun takes to start from a node and come back to that node again. So the sun takes sidereally is about 365.25 days. But then the nodes do precession, they regress, right? They have retrograde motion. So they take 18.6 years to complete one cycle. So in a year, they travel about whatever, roughly 20 degrees, right? That 20 degrees results in this diminished number compared to 365, right? So this results in a pattern known as eclipse season, right? So if you divide, because we have nodes on both ascending, descending nodes, we get a typical pattern that every 6 months you are likely to get an eclipse, right? That's what I've seen. There'll be some eclipse of some sort happening somewhere on the Earth, either solar, lunar, correct? That is a pattern we see, and that is because of this. And pattern, right? And the pattern is also such that if you get a solar eclipse, 15 days from that time, you may get a lunar eclipse or the other way around, right? So the eclipse happens first in one node, ascending node, and after 15 days, it'll happen in the descending node or other way around, right? So in fact, 15 days from now, there is a solar eclipse happening. I think it is on 21st or so, but it is not seen from India or the American continent or Europe. It is mostly seen from the Antarctic side. Okay. But there is one. And we also seen this pattern of 6 months. 6 months back, there was a lunar eclipse in March. All right. So you can work out a pattern, right? You ask Stellarium to predict all the eclipses for 100 years, 20 years, whatever it is, and get, right? So it's typical frequency, right? If you take solar eclipse, one eclipse season, at least one, right? Or two. One eclipse season is like 30 to 37 days, correct? So in a year, right, at least two. You will get at least two solar eclipses. People might find it maybe difficult to believe, but that is the case. Why? Because solar eclipse will happen, but you will not see it, right? Solar eclipses are location specific. You have to be in that place to see it, but definitely the moon shadow is falling on the earth somewhere. Because you're not there, you don't get to hear about it, right? But they do. In fact, solar eclipses are more frequent than lunar eclipse because of a certain geometry which will come, right? Lunar eclipses, roughly, you can say if you take a century of 100 years, you will get around 230 eclipses, right? 2.3 eclipse on an average per year. But there will be years where there is nothing. There will be three. Some years there will be three, but typically two, right? Averaging out to 2.3. That's a pattern. So why this pattern? And this is coming back to the geometry again. So how do we predict? So with Newtonian mechanics and everything, what we look for is where, is there an obstructing these disks, right? Solar disk and the lunar disk, are they obstructing somewhere on the path, right? So we look for not just perfect alignment, but partial alignment like this, so that we can get to see an eclipse. So that depends on how far the moon is, how far the sun is, what is the tilt, how close it is, all that. All right. And this node, which you talked about, that also precesses, so that also matters in the computation. Okay. And why I made a statement that hey, solar frequent eclipses are more frequent. This is the reason. So this is an extreme case A and B, right? The lunar shadow falls on the edge. It falls on the edge. So you get all this region for a solar eclipse to happen. Look at that region A to B. This arc is wider, is more. It has more angle compared to this arc where lunar eclipse is happening only between C and D. Why? Because this shadow, this cone is tilted, right? It is a cone with a 0.5 degree apex angle, right? So this length is less than this length, angular length, right? Angular arc measure, right? So you get more solar eclipses. Interesting fact. So that completes all the general stuff about eclipses. Now we will quickly cover what's there tonight. So Nandan, do you have any questions?
No, not yet.
Not yet. Okay. So today's eclipse, in context, right? So I just asked Stellarium, how many eclipses we can get 2010 through 30, about 20, 21 years. Okay. And it gave me this figure, right? So there are two total points here. The one is the total phase, right? Total eclipse, and this is the sum, right? So we have about 48 lunar eclipses over 20-year period, right? Roughly 2 plus, with a division like roughly 1/3 penumbral, about 25% partial. That will add up to whatever 29. The remaining 19, right? About 35% is total. Okay. But from Bangalore or India, you can see it, you may not be able to see it. What is the divide, right? So we get to see about, it's only 6 out of the 19, 1/3 we can get to see, or which are good or perfect visibility aspects. 13 are bad, right? So this is the kind of ratio you get. They're no hard and fast, but if you take a long enough period, you get a rough, probability over the years, right? And that remains. If you take a long period, it remains. So that's why we say 2.3 eclipses, lunar eclipses per year, roughly on an average. Last one was 18. Okay. So it so happened that the probability was such that, we have to wait almost 7 years for the next one today. But the very next one, right, is not that far. It's just 3+ years from now. Right. So what to see tonight, hoping weather is good. So this is a stellarium screenshot. What you're looking at is toward the southern horizon. I'm showing a wide angle so that on the left extreme there is east, southeast, south, southwest, and west. The moon rises from the east, goes all the way like this, all the way like this. In that, at about 10 p.m. or at an altitude of 50 degrees and southeast, roughly southeast, with an azimuth of 170 degrees, we get the partial eclipse start. It progresses into full eclipse by 11. Totality starts. Peak is 11:42. Exit at 12:23. 1 hour 23 minutes. All right. And then we have the egress phase that ends at 1:27 a.m. So it has crossed the meridian by that time. Okay. It crosses somewhere in between. The totality ends just after crossing. So that also means, you can, the anti-solar point, right? A point opposite the sun is right here when that happens, that traverses, obviously, as Earth rotates. And the moon races around, crosses the shadow, and you get this whole sequencing. All right. And typically, if you look at the NASA website, you will find a diagram like this. So this shows you how the moon traverses across the shadow. So the red is the umbral shadow. This is the lighter gray is the penumbral shadow. So it doesn't go today all the way through the center, but roughly, somewhere between the edge and the center. So we get about 1 hour, 22 minutes in this path. Okay. There are longer ones. 1 hour, 47 minutes is the longest. So that is, will be traveling right through the center. But today we have 1 hour, 27 minutes. Long enough time to enjoy it, providing weather is good. I put all the times here. All right. The azimuth and other things. This is a typical part of the, how do you characterize eclipse? You put this diagram, you label the contacts, and you get the, description of the eclipse. As Nandan was saying at the very beginning, very safe to watch with naked eye. Best seen with naked eye. Very dramatic views, wide-angle views. Absolutely no protection needed. Absolutely safe to eat anything you want. Enjoy the eclipse. You can use binos or telescope if you want to look at finer details of the shadows in action, hues, subtle contrast, right? You can use ping, that is good. But in general, you can just look up at the night sky, enjoy, right? So that's the end of the session. So if you have any questions, we can take it. If you want to see some demos with Stellarium or how to play around there, want to know some resources, that also we can do. And then you decide what we can do.
Yeah, Shankar, we do have a question. Jagan Mohan is asking this question. Let me read it out. Given the orbit and inclination of Moon, Sun, and the Earth, which do not change, why is it that we don't see similar eclipse cycles over a period of time?
Can you repeat that?
Yeah. Given the orbit and inclination of Moon, Sun, and the Earth, which do not change, why is it that we don't see the similar eclipse cycles over a period of time?
Okay. In fact, we do see very similar eclipse cycles if you take a long enough period, right? So there is a cycle called Saros cycle. Okay. So that Saros cycle considers all aspects into consideration, and it's a long period of roughly 18 years, where after that cycle, right, you see exactly the same geometry for eclipse occurring. So what happens is, you get a very, very similar eclipse in geometry exactly after that one Saros cycle. Okay. And the same thing repeats. So now there are different such Saros cycles running concurrently, right? So if you take this eclipse and the next eclipse and the next, right? They all belong to different Saros numbers. But if you take within a Saros, exactly after that period, the exact geometry repeats. So, and that is because, of the dimension. So what complicates things is that, in fact, things do change. Whatever aspects which he has mentioned, they do change. So there is a slight variation between one cycle to another. That's what I was saying earlier, that, you might say new moon to new moon is on an average 29.5 whatever days, right? But that is on an average. But if you take one month to another month, one could be 29.4 days, another could be 29.6 days. Why is that? That is because of perturbations from other planets, from the orbit. It's not a two-body problem, right? It's a multi-body problem, with the sun mainly perturbing the lunar orbit. So you get different, changes in every cycle. There is Jupiter pulling onto the whole system. So there is some other change. The orbit is not, it's an ellipse, right? So that means the distance is not exactly the same. So at perigee, you're closer, right? And then at apogee, you're longer. That will change the way whether it'll be an eclipse or not, whether if you take a solar eclipse, right, whether it'll be annular or partial or full, right? So multiple aspects coming together, and things are always changing, correct? Earth itself is orbit is precessing, right? So that is a change. That's Earth-Sun distance changes. So you may not get exact geometry in a simplistic way, but on a very, very large scale, you do get. right? If you look up, read more around Saros cycle, you will know that, hey, there is a pattern. That's why, the older times predictions were made, which are reasonably accurate, right? So there is a pattern, but on the small scale, it is not observed as much because of all these changes.
Okay, thank you. So about the cycle, can you spell that? Saros cycle, can you spell that,
Saros,
please?
SAROS.
Saros, Saros
Yes.
cycle.
Yes.
Okay. So we have a eclipse happening tonight in 2025. So 18 years from now, in 2043 or so, is it safe to assume that we'll see a similar?
Yes. You can look it
Okay.
up. Yes.
Okay. All right. We have another question here. Okay. Why is unique? Somebody called Unique is asking this question. Why is the Earth's orbit around the Sun elliptical instead of perfectly circular? According to Einstein's space-time fabric idea, shouldn't it form a circle?
No, general theory of relativity doesn't have any such restrictions. It all depends on the initial conditions, right? So how did the Earth orbit form, right? Initially, there was a protoplanetary disk rotating around, all that disk, were remnants of maybe a stellar explosion. There are all sorts of liquids in different shapes circling around sort of a proto sun, and they eventually set it into orbits, right? The planets formed, they eventually set into orbits. So there is no restriction which Einstein has placed or Newton has placed. In fact, the circle is very restrictive. A natural fit of an orbit, a stable orbit, is an eclipse, because you can have so many kinds of eclipses with different shapes, different eccentricities, right? Different elongated. But circle, you have to get it right. Eccentricity is zero. You have to get it perfectly right. That you will never see in real world. You will either see, if it's a stable orbit, you will see eclipses, or you will see parabolic, hyperbolic orbits.
Right. There is another question about meteor showers. I'll go ahead, although it is slightly off topic, I'll go ahead and ask that. Why do more meteor showers occur in December? Does the Earth cross the same asteroid's path every year or different asteroid paths?
Yeah,
I know this is slightly off topic, but since this is astronomy related, I thought we'll take that.
Sure. So the meteor showers, right? So I don't know about whether December is a peak or not. I don't know that. But then I can definitely tell you that meteor showers happen when Earth crosses the path of a
Right.
dead comet, right?
Right. What the
Dead
remnants
comet,
of Earth, right?
the remnants of a dead comet remain in the orbit. So there is a cloud, right? There is an orbital cloud. So along the whole orbit, right, you will find debris which has shed by a disintegrated comet, right? So that cloud keeps rotating, keeps circling the sun in its elliptical orbit, whatever orbit, right? So there's a cloud. This cloud, go across it, right? So uh, and and it all depends on the geometry again, right? So if it
Exactly.
so happens that you cut across in December with a thick cloud of debris, and that angle of the attack is in a good viewable geometry, you get good meteor showers. That's it.
Oh
That's
yeah,
about it.
yeah, that's absolutely right. Plus, if there isn't too much of light around, I mean, if there isn't moon hanging around, you tend to see more meteors that night. So,
Absolutely, yeah. Right.
okay, I think that's about all the questions we have.
All right.
We any more questions, anybody? Please go ahead, ask on the YouTube channel. Okay, there is another question from Krishna Kumar. Why don't we see lunar eclipse every full moon? Okay,
Yeah,
this
that was
question was
answered at the
answered
beginning.
earlier,
This was answered at the very beginning.
but maybe, I don't know, maybe Krishna joined later.
Yeah.
If you could just quickly run over that explanation.
Yeah, so the essential reason is the tilt of the lunar orbit, right? So because of the tilt, even though you will have a full moon, right, which is like exactly opposite in terms of ecliptic longitude 180 degrees. But if you take latitude, no, it won't match. It is not a clear straight line and you won't get an eclipse. It's primarily because of the tilt of the orbit.
Yeah. So hope that question is answered, Krishna. There is a tilt between tilt of about 5 degrees between the lunar orbit and the ecliptic. That is one of the reasons why we don't see an eclipse every full moon. There is another question from Renuka, a class 10 student. My dream is to join IISc Bangalore. I strongly admire physics, but my math is a little weak. Could you please guide me on how to start preparing from now?
Work hard. That's just a two-word answer.
Exactly.
You will get there
Fall,
for sure.
fall in love with physics and math.
Great.
Uh, okay, I think that's about it. That's about all the questions we have. We can give another minute or so
Sure.
if anybody is
Yeah,
thinking of asking a question or not,
absolutely.
you can give
Right.
it a minute or so and then
Mhm.
wind things up.
Yes. So, for people who are familiar with Stellarium, I will, while we wait for a couple of questions, you can, in fact, predict eclipses in Stellarium and you can get to see all the list. So, you can see today's eclipse, March. For today's eclipse, you can click where it enters penumbra, and in Stellarium, you can mark the umbra and penumbra regions. Okay. And if I run this, you get to see the eclipse happening, crossing penumbra, umbra. Now even Stellarium even renders the sky with more stars because there's no moonlight. Now it's disappeared. Comes out the umbra, comes out of the penumbra. Right? You can play around and get to know more. Great tool. If you're not used it, please do use.
And the best part about Stellarium is Stellarium Web at least is free.
Mm.
It's
Even
a
Stellarium, I thought it
freedom.
was free. The desktop version is free.
Stellarium desktop is free. Yes, exactly.
Yeah, Stellarium desktop is free. Stellarium mobile on Android, iOS, that is free. Very, very one of the very beautifully made apps. What else?
Jagan is asking another question. Can you
Mhm.
show the workflow in Stellarium of how to simulate eclipses?
Sure. So yes, so let's get there. So I'm in Stellarium. All right. I picked up whatever place, Bangalore, right? Now on the left side menu, you open this astronomical calculations window. Okay. So I'm going to clean up. Okay, I can pick. So you open on the left side, astronomical calculations. There are multiple tabs here. You choose the eclipse tab. From here, I can put 25, 24, whatever, right? So I just put 2 years and I picked up a selection of penumbral, partial, total completely, right? I can choose whatever I want. On the bottom, you can see all solar eclipses, local solar eclipses, lunar eclipse, planetary transit. Different phenomena are there, right? So I pick lunar eclipse. I selected that. I can pick solar. Now I pick lunar, lunar. Then I will just say compute, calculate eclipses. So in under like a couple of seconds, it has populated this entire list. On this list, if you see 2 years, right? The 2 years it has made 3 plus 3, 6, 8 eclipses. 3 total, 3 penumbral, 2 partial, right? And it also tells you what is the visibility. So perfect visibility for today, except that it doesn't consider weather, right? But for the weather, it's perfect because it's visible very well up in the zenith. No obstruction from India, from my place. So if you select that on the bottom panel, you can see different events of the eclipse, right? I mean, enters penumbra, enters umbra, totality, beginning, max. So you can get different events. And then what do you see, right? So you pick up moon here. So let's say let's point somewhere, right? I select moon, control F, search for moon. It will pan there. I can set whatever way I want. And then if I put, if I double click here, it will go here, right? If I want to keep the moon in the center, I click moon, press space bar, it will be in the center. I can double click each of the events. It will take me there, right? Then the next question is, how do I get this line, right? How do I get these circles? So there is another trick here. So there is this settings window, right? This is a view setting. I get it by function F4. So in that, you go there, go to solar system objects, you take the orbit, lunar orbit, just to see how it transfers. So see, the red line disappeared. Click again, it comes back. Okay, it's over the lunar orbit. All right. And then what do you do? Then you come to maybe markings. Okay. In the markings, you pick on the very right side anti-solar point. That's a point exactly opposite the sun. Earth umbra, Earth penumbra. So you can see that that those things disappearing once I unselect. So let me do that. So now I remove the anti-solar point. The ASP disappeared. Earth umbra, that is gone. Earth penumbra, that is also gone. Okay. I will bring it back. So they let you see the moon, relative to the shadow, right? So you enable this, then you got those circular points. And if you want to create some sort of animation and all, what you can also do is
Can we do that for one Saros cycle?
one Saros cycle is very long, correct? So
Yeah, that's what I was
you will not be
explaining.
able to
Yeah,
do that way. Yeah, you won't be able to do that. That is too long. Maybe you can script it. There is a way to script in Stellarium, so you can write sort of JavaScript code and do that, but not easily in this way, right? Yeah, so I will look at back again at southeast. Where is the moon? Here it is. Okay. Right. So you can do that. Or what you can also do is, the screenshot which I captured was done in this way that let me turn off these points. Let me set an earlier time. Here. Let me set it up at 6 o'clock. Okay. So moon is about to rise. You can see just about rising, right? And you can just animate it very fast. Correct? You can do that. But then what's at this wide view, this moon is very small. But Stellarium has another option, where you can actually draw it at a scale for see if I pick this, see the moon becoming big. So I can put any scale just for the moon or the planets. I
Oh,
make
this
it
is useful. Oh, this is
8
nice.
times. Yeah. So now if I do that, now if I run it, you can see a beautiful, beautiful movie being made. All right. So now I'm zooming in.
Ah, there you go. Yeah.
Eclipse. There, exit. So you can see it that way. So moon is enhanced. So you can do the same for planets also. So there is a Saturn. So if I were to do the same planets, right? So see, it is bigger. I can make it even like 1,000, I think. I don't know, 1,000 is maybe 100, 99, 500. Yeah, I can make it 500. So Saturn appears big
Mm-hmm.
than the usual, size, relative size, right?
Yeah.
So all this you can do.
Oh, if it's cloudy night, if it's cloudy tonight, this is what I'm going to be doing then.
Yes.
Can't,
You can simulate. Yes, exactly. You
yeah.
can simulate. And also, you can set the atmosphere on off. So,
Mm-hmm.
that obviously many people will know. I just press A, keyboard A.
Right.
Now there's no atmosphere. So I can, it simulates the Milky Way better. But if I put, there is atmospheric, seeing is bad, right? It reduces the seeing, right? So
Yeah.
Milky Way is not very clear. You can also make the ground disappear. Press G, ground disappears. G again, it comes
Yeah,
back.
switch
You
on,
can do
switch
all
off
these tricks.
horizons. Yeah.
Yeah. So it's a very, very useful tool. Great educational tool. All right. What else?
Okay, there's another question here. Can one Payal Patki is asking this question. Can one calculate orbital dimensions from time duration of lunar eclipses? I'll repeat that.
Yeah,
Can
we can.
one
We can.
Oh,
We can.
okay.
But you have to make a lot of assumptions. Then you can roughly you can. So you have to know X to do Y, right? So rough calculation, right? Let's do a rough calculation. So as I said, the max eclipse, right, is about 1 hour 47 minutes totality. How do you get that? How do you get that? So you get that by, and I also said, the umbral shadow is about 2.7 times the diameter of the Earth, right? Angular diameter is 2.7 times the lunar diameter.
Yeah.
So with these, right, you can do a proportion calculation. So 2.7 is, I say, 1.35 degrees, right? So 1.35 degrees out of 360. So if it takes 1 hour 40 minutes to traverse that, how long does it take to traverse the full side, right?
Okay.
You can do all those ratio proportion calculation and you can arrive at rough figures.
Yeah, reasonable ballpark numbers at least you
Yeah,
can arrive
ballpark
at.
numbers you can.
Yeah. There is another question. Okay. We all know about the Aditya L1 mission. What is L1? Is there
Yeah.
L2, L3? Why
Yeah.
null?
So,
I mean, what is specifically L1? The Lagrange points I think he's talking about.
exactly. Yeah. He's talking about Lagrange point. So, L1 is a sort of a location in space. It's called a Lagrange point one. Okay. So there are like 5 such points, L1 through L5, I believe, right? So these are points with special properties in terms of gravitation. Okay. So we all know that Kepler's laws, right? So he has 3 laws, and one of the laws talks about the relationship between period of the planet versus the distance, right? They are in a specific relationship, right? Something like cube of the distance is proportional to the square of the period. Roughly, very, very roughly, right? You get longer and longer periods as you go away from sun. So Earth is 1 year, Mars takes longer, Jupiter about 12 years, right? Saturn 30 years. You get longer and longer. So suppose you imagine a spacecraft which is between sun and Earth, right? It will take less time, correct? So maybe suppose it's only somewhat less distance from Earth, it's close to Earth than to the sun. It might probably take 11 months instead of 12 months. Suppose some other spacecraft, it might take 13 months. But then there are points which fall somewhere between Earth and Sun. If you place the orbit there, it will rotate the Earth in such a way, it rotates the Sun in such a way that it takes exactly the same 12 months, even though it is closer to the Sun. That point is L1, Lagrange point. It is because of it's not a two-body problem, it's a three-body problem, mainly Sun, Moon, and Earth playing on the orbit. And because of that, there are these quasi-stable points where it moves along with the Earth, but at a much, much larger distance, right? Several million miles away. So they gives a convenient spot to talk to the Earth on one side and talk to the Sun on the other side. So if you want to observe Sun and conveniently, talk to the Earth on the other side, this is the right place to put the satellite.
Yeah, yeah. This is probably like geostationary orbit, but not at 36,000 kilometers, but at a few million kilometers. It's always Earth
Oh,
facing.
tough. Of course, they have analogies break. Yeah, but geostationary, they rotate Earth, but then this craft rotates the Sun, right? It in fact rotates the point around L1. It's in a loop, something called Lissajous loop around L1. Orbits are different, but you at least From the point of view of the orientation with respect to Earth center, yes, yeah, you can compare, but the comparison is not applicable beyond that.
Mhm. Okay, I think that's about it. That's about all the questions that we have. So thank you, Shankar. Thank you for the talk, and thanks for everybody who joined this talk on YouTube. I hope you found the talk educative. Yeah, I hope you found it insightful. So, as far as BAS is concerned, Bangalore Astronomical Society is concerned, we will keep organizing talks just like the one you just heard every so often. Information about this will be posted in our social media handles, on our Telegram channel. It'll also be put up on our website. If you wish to join our Telegram channel, just visit our website, which is bas.org.in. I'll repeat that, www.bas.org.in, and in there you will find a blue button which says join our Telegram group. Please do join our Telegram group from there. We're also present on Instagram and on Twitter, and of course we are on YouTube. So once again, do not miss tonight's lunar eclipse. Hopefully the weather will clear up, and hopefully we'll be able to view the spectacle. And yeah, wishing everybody clear skies. Once again, thank you very much, and goodbye. Thank you, Shankar.
Thank you, everyone. Have a nice evening, and let's hope for clear skies.